All right, here we are on top of a dune overlooking Lake Michigan. And what I like about this spot is that I can see both the eastern horizon and I can see the western horizon. So I thought this would be a nice place for us to be able to try to visualize the two coordinate systems that we've encountered, the horizon coordinate system and the celestial equatorial coordinate system. So let's take a look at these two. And I've brought with me a hula hoop to try to help illustrate kind of where these lines are on the sky. The first one in our horizon coordinate system is pretty easy to see because we're familiar with this idea of the horizon, right? I can see the line of the horizon all the way around me. And I could use the hula hoop, if I place it over my head, I could use the hula hoop as kind of like representing that horizon line all the way around me. And when I count up around the horizon, that's where I get this kind of weirdo coordinate that we've been introduced to do called the azimuth. Now this is north, and so this point on my horizon circle would be an azimuth of 0. And as I continue to increase to the right, my azimuth increases until I get east, and then I have an azimuth of 90. So if I were to say, okay, I have an azimuth of 45 degrees, it would be halfway between north and east, so it'd be right about here in the northeast. Likewise, I can keep increasing all the way to the south where it's 180 degrees and to the west where it's 270. And so you start to get that picture of how this horizon all the way around us is like a circle, just like a hula hoop. And I can count the angle from 0 all the way around back to 360 degrees. Now that's helpful when we want to know what direction in the sky am I looking from this location. What direction do I have to look? It gives us a high degree of precision besides just saying like, hey, look towards the northeast. I could say, no, it's 47 degrees instead of 43 degrees. It gives me very high precision. Likewise, the other horizon coordinate is the altitude. And so I can kind of visualize this as well with my hula hoop, putting my head somewhere in the middle, that the horizon is like my 0 point, right? My 0 altitude. And I count up on this angle as I get to straight overhead 90 degrees. And so again, I can use a precision degree to tell me exactly how high I need to look in the sky, right? So with two numbers, a azimuth, like let's say 260 degrees, boom, and an altitude, like let's say 15 degrees, I have a very precise point in the sky. So I could say, wow, do you see that supernova that's at 260 degrees azimuth and 15 degrees altitude? And that'd be great if I have someone else who's standing right next to me right now. But if that other person is located anywhere else on Earth, or if any time goes by, that coordinate is no longer accurate. And that's because, right, the sky keeps moving. The sky keeps moving. So even 5 or 10 minutes later, that supernova in the sky is going to have drifted along with the entire sky closer to the west. And now I need a new position, right? So altitude and azimuth is really helpful if I'm talking to someone, another observer right next to me right now. But the equatorial system, that celestial equatorial system, is way more useful for astronomers because that whole system moves on the sky. So what we need, right, is we need 0 points that are fixed relative to the Earth, right? Fixed relative to the Earth because obviously the sky's not moving, it's the Earth that's rotating. So if somehow we could fix our 0 point, instead of a horizon that depends on an individual observer, if we can fix it to the Earth, we're all set. And that's where the idea of the celestial equator becomes really useful. So that celestial equator we've seen is this idea of the Earth's equator extended out into space. But on the sky, what that looks like is instead of a horizon as our 0 point, we have the celestial equator. And if I could draw that on my sky, because of our location, my location right now, it would look more or less, let me find it pretty close. It'd be basically like this. Okay, it would be crossing my horizon at due east and due west, but it would be tilted. And the amount it's tilted depends on where you are on the Earth. So if I was on, let's say, the equator, it would be tilted all the way like this. The celestial equator would be straight overhead and straight east and straight west. If I was located on the North Pole or the South Pole, the celestial equator would be right on my horizon. But since we're somewhere in between, it's kind of tilted. Now this is our celestial equator, and now we have these two other dimensions that are measured relative to this, these two other coordinates. So along my celestial equator, sort of the equivalent of like azimuth, and we saw this is also like the equivalent of longitude on the Earth, we have right ascension. So as I go across and along, I'm going along my celestial equator, I have increasing right ascension. Increasing right ascension. And the beauty of this is if I have a particular right ascension, let's say 1 hour of right ascension, that as time goes by, that moves across the sky. So if you were to tell me right now today, the sun, I'm going to kind of block the sun right there because it's so bright. If you told me the sun has a right ascension of, let's say, I don't know, 6 hours, 32 minutes today, all right, well, at sunset, it's still going to have a right ascension of 6 hours and 32 minutes because it stays at that same spot, more or less, over the course of a day, right there on our celestial equator, right? So this whole system is rotating with our sky, so that's going to be an accurate number. Now, and it will stay accurate for any observer anywhere on Earth and at any time, right? Unless that object is moving, like, you know, planets and stuff. Okay, and then our other dimension, our other coordinate is going to go like this, increasing, right? So I have my celestial equator, and the sun's going to kind of get in my way here. Here's my celestial equator across the sky from east all the way across to west. And now I'm going to twist it, right? And here's my increasing declination. So my celestial equator is that 0 point, and I can measure declination going up. I'm tilting way back now, all right? Or I can measure that declination going down. And you can see right now that the sun's declination is a little bit below the celestial equator. And that's because it's in the fall, so it's heading towards winter, and the sun is on its way lower and lower in the sky. All right, and if I were to twist myself around and look towards the north, right, the declination, the very top of declination would be 90 degrees, which points right towards the north celestial pole, or Polaris in our case. All right, so that's how we can visualize these things on the sky. These are lines going across our entire sky, right? But the key thing for us to take away at this point is that the celestial equatorial system, what it's doing for us is it's giving us a coordinate system that is fixed to the sky, so that as the sky moves over the course of a night, as the Earth rotates, those coordinates are not changing for the stars. Okay, I hope you found that useful. If nothing else, it's a pretty view of Lake Michigan. All right, we'll see you next time.